Good morning, everyone, or greetings for whichever part of the day you're in, wherever you're coming in from. Now, for this full moon session, we're going to look at various lunar divisions of the circle. Now, before we look at that, I'll show a few slides as usual. Now, this is a very subtle image. You might need to look at your computer screen from a particular angle, but this is a lunar halo. I took this photo just after I finished the session a month ago, in fact. There was a wonderful halo around the moon. Now, when the moon is full, obviously, most things are sort of bleached out of the sky because there's so much light being reflected off the moon. But in this particular image, and at this particular time, 1 month ago, Jupiter was very close. So you can see that small white dot there. Now, for something to be visible so close to the full moon means it must be really bright. And Jupiter is, in fact, the second brightest, small star-like object after Venus. Now, I took another image with a sort of night filter. So if you couldn't see that last image, this is another version of that halo. You can see it's got a slight rainbow color to it up at the top. Now, with these images of heavenly circles, let's look more at the circle and the various divisions that one can make of the circle. Now, I've talked a lot about these rational divisions of the circle. I'm going to talk a bit more about them because they have really, it's an architectural usage that they have, and that's what I'm going to show you a bit later on with some of my research about cathedral design from my book, The Cosmos in Stone. Now, the really commonly used one, the one that I think I showed you a couple of weeks ago, which works in relation to John Michel's remarkable diagram of the Earth and the Moon, is 22/7. Now, 22 divided by 7 equals this. Now, it's a number that goes on to an indefinite number of decimal places, but it goes into a repeating pattern. So you can see the way I've coloured the numbers there. You have this repeating decimal of 142857. Now, this means that it is actually a rational number. Now, here's another one, 864/275. Now, the higher the numbers are in your sort of rational approximation of an irrational, the closer you can get. So, for instance, this is a version of pi that Fibonacci used. Leonardo of Pisa used Fibonacci, hence the Fibonacci numbers. He's the one who is associated with talking about them in one of his books. Now, 864/275, as you can see, it goes even closer. It goes to 3 decimal places of pure pi, and it goes into this repeating decimal of 181818. Now, pure pi, as I've mentioned before, it's incommensurable, irrational. So it goes on to an indefinite number of decimal places, but without going into any sort of repeating pattern. So I suppose you could say it's a number that is ultimately unknowable. Whereas we can know the rational numbers, we can't know rational numbers in the sense that they go on to an indefinite number of decimal places without going into any sort of repeating pattern. Now, 864/275 actually shows itself in relation to the size of the moon. Now, I sort of briefly went close to some of this a couple of weeks ago when I showed John Michel's pattern of the Earth and the Moon. I didn't talk about the mileage measurements. I'll do that at another time. But if you use the so-called English mile, then you get these very beautiful and sophisticated number patterns. And so what can be suggested about the English mile is that it's not English, it's not an English invention, it's a cosmic unit. So it's a naturally existing cosmic unit. Now, in terms of the English mile, it's given a date when it, I suppose, becomes codified or when it comes into being as an official measure, but no one really knows where it comes from. And this is often the case with these measures. They perhaps become officially recognized at a particular point, but no one really knows what has led to them. And so there's always a certain mystery about where these measures come from. And it so happens that when you use the English mile, you get a lot of very interesting number patterns with the size of the Earth in relation to the size of the Moon. Now, those of you who've seen my talks before, or if you're aware of John Michel's research, you'll be well aware of these mileage measurements. Now I'm going to show you one in relation to the moon. The moon has a diameter of 2,160 miles. And we'll look at this in relation to 864 over 275. So let's derive our circle from the moon, 2,160 miles. Now I'm going to divide the circle into its four quarters, you could say. So you see there's those four right angles now produced in the middle of the circle by putting in the vertical and the horizontal line. I'm going to flip those four quarters out so that those four 90-degree angles end up in the corners and we get a square. So we have this squaring of the lunar circle. Now, again, this square has an edge length of 2,160 miles. So we can say that the peripheral measurement of the square, put that in, is 4 times 2,160, which is 8,640. So there you have the 864 within the pi measure. Now, the next thing I'm going to do is actually do a proper squaring of the circle. So in goes the circle. Now, this circle, if looked upon as having a rational circumference, has the same peripheral measurement as the square. So this circle also has a circumference of 864. So there you have that larger number within the pi measurement, because obviously the larger number in a pi measurement denotes the circumference of the circle. Now, the diameter of this circle is inevitably going to be 2750 because of that approximation, 864 over 275. So if you square the circle of the moon, then you get this particular measure if you're using the English mileage. So this is just another example of these concordant numbers that you get cosmologically if you're using the English mile. Now, this measure is actually used in the chapter house at Wells Cathedral, which is where the moon square is used within the diagram. So that's almost another confirmation that it is this lunar area. Now, this idea of rational and irrational numbers leads to a very interesting philosophical area, because of course rational numbers are numbers that we can know, whereas irrational numbers are beyond what the human mind has the capacity to know. Now, this is something that's actually stated just very directly in the medieval encyclopedia known as the Etymologies. It's really the encyclopedia of the medieval age, found in every library that you'd go to, written by Archbishop St. Isidore of Seville. Rational magnitudes are those whose measures we can know, and irrational, those the amount of whose measurement is not known. Now, he doesn't go into this sort of philosophically, he just sort of states this in relation to geometric forms and how they contain. So, for instance, if the edge of a square is 1, the diagonal is the square root of 2, which is an irrational. Now, let's now look at a Pythagorean idea. And this idea of the bounded and the boundless, or empyron and apeiron. Now, this is what you find in the fragments of the first Pythagorean who wrote anything down, because Pythagoras himself didn't actually write anything down. Now, Philolaus, the Pythagorean, this is at the beginning of the fragments of his written work. Nature in the world order was fitted together out of things which are unlimited and out of things which are limiting, both the world order as a whole and everything in it. So there we've got sort of a similar, perhaps more philosophical idea, which is expressing this same principle that you get in mathematics of the rational and the irrational, or the commensurable and the incommensurable. In the first few sessions, I think in the first session and the third session, we're in the fourth one now. So in that first session, we did a hendecagon, an 11-sided or an 11-fold division of the circle, and then we went on to 22. Now, you may remember that what we did was to look upon the radius of the circle as being divided up into 16, and then we could take 9 of those 16 units to get the edge of an 11-sided shape. Now, we drew polygon stars. Now, as I say, it's not a rational measure if you're doing it, if you have the pure radius to edge measurement of an 11-sided shape, it's not rational. But we can approximate with this 9/16 of the circle. Now, the one that we did last time, the heptagon, that's dividing the radius into 15 and then taking 13 of those units, and we get a very close approximation of the heptagon. Now, as I mentioned earlier, these rational divisions of the circle, I mean, you could use them if you're drawing patterns, but really the place where they belong and where they really are used a lot is in architecture, in the sense that you can't have a massive pair of compasses that does a vertical measure of, say, an elevation of a building. So you build in rational units, but also more philosophically speaking, this in a sense is the bringing of the heavenly form down to earth in its, I suppose, rationalized state. It's a humanly comprehensible state. Now, this is what I'm going to show you in relation to the Wells Cathedral, which is this building I've sort of done so much research on for my book, The Cosmos in Stone. Now, we're going to look at the octagon, and there's a very interesting use of this type of measure within an octagonal area in the cathedral. Now, if the radius of the edge, or if the radius of the octagon is 1, then the edge length is this incommensurable number here, 0.765, 366, 865, it goes on. So let's look at that in relation to the octagon. Radius is 1, and therefore that is the edge. Now we can do a rational approximation of this if we do 153 divided by 200. So if you divide 153 by 200, you get simple 0.765, and that's it. So the numbers stop just there. So if we apply that to the octagon, you see that if the radius of the circle that contains the octagon, if that is 200, then the edge length will be 153. As you may be aware, quite an interesting number in the Bible in relation to the 153 fishes. Now, this is the area that this particular approximation is used in. Now, we looked at this area a month ago when I showed you Jean-Michel's diagram. And what we actually looked at then was in this octagonal area that's at the center of the circle, we looked at the room that's above it. What we're looking at now is the undercroft, which is below the chapter house. So I'll show you what we looked at a couple of sessions ago. This is the chapter house. The octagonal area at the top now is actually the chapter house, and that's where the moon square fits. It's the same pyramid triangle, but this is using it in the form of Jean-Michel's diagram. Whereas this one that we're going to look at now, the undercroft, it's a different room and it's a different geometry, but it uses the same pyramid triangle. Now, within the pyramid triangle, you can see how there's also a pediment-shaped triangle down at the bottom, and that's what's defining the size of the circle. Now, this version of the pyramid triangle is actually different to the one used in Jean-Michel's diagram. It's actually a golden ratio version of a pyramid triangle, which is virtually identical to the one that's used in Jean-Michel's diagram, which has a base of 11 and a height of 7. Now, in this golden ratio version of the pyramid triangle, if the base is 2, then this is 1.618, which is that golden number. That's 1.618. Now, that's the pyramid triangle. But if we look at the pediment-shaped triangle, which I've mentioned in my book, and I've called it the golden pediment triangle, because it has a baseline of 3, and then these are 1.618. Now, the interesting thing about the interaction of these two triangles is that they give a very close approximation of pi, in the sense that if this is 1, the height of the pediment triangle is 1, then the height of the pyramid triangle is 3.1451. I think that's it. It's a really good approximation. Now, in this particular instance, what we're going to do is say that the radius of the circle is 200. So this reflects what we were just looking at with that 200 to 153 measurement. So let's say that, part of this pyramid triangle, that gives us a radius. So we'll say that this is 200 units. Now, in goes the octagram star. Now, you can see how the octagon at the center of the octagram star very accurately defines the octagonal space of this room. And it does very much so. When you measure it, you get this very precise, it's 51 feet from wall to wall, very accurately so. Now, let's look at how we get to that 51. Now, if the green radius here is 200, then obviously the 8-fold division of the circle, which is what this 8-pointed star gives, the distance between each of these stellations is going to be 153 if we're using this approximation. Now, what then happens is that if you divide that 153 by 3, you obviously get 51. So this is how you can suggest that this approximation is being used, because it's so very close. It's just a division of the 153 by 3. Now, if we're going to divide the 153 by 3 to get 51, then obviously we need to do the same thing with the 200. So the 200 gets divided by 3, and that gives us the actual footage of the radius of that circle, 66, and it's actually 66 feet and 8 inches, because obviously that's 2/3, the 0.6666. Now that measurement, 66 feet and 8 inches, is basically exactly the same as the size of the dome in the Dome of the Rock in Jerusalem. Now, one of the things I've mentioned in my book is how this octagonal area of the cathedral appears to be an image of the Dome of the Rock, which at the time that Wells Cathedral was built was known as the Temple of the Lord, and it was a Christian church because of it being the Crusader era. Now, more about that in the book. That would be too much detail to go into now. Now, if we take this measurement if you look down in the bottom left, 66 and 8 inches, 0.666, if you take that and you multiply it by the 0.765, you get the 51. So this is how you get these sorts of rational divisions of the circle that are used in architecture. And so you can mark out in rational units. And so in that sense, the circle becomes squared and heaven descends to earth. Right, the numbers we're going to look at today with our drawing, they're all lunar numbers. And again, they're ways in which you can use the radius of the circle rationally to get your edge. Now, we looked at 7 last time. This week, we're going to look at 14, which is the number that's associated with the full moon. The full moon, today's full moon, and we're about the time of, yeah, it's pretty much the full moon right now. It's around about 14 3/4 days. So it's between the 14th and the 15th day. And both those numbers are associated with the full moon. Like 15 is sometimes a day associated with the full moon as well, the 15th day of the lunar cycle. Now, the other number is the whole lunar cycle, which is 28. Now, that's a sort of, you could say, archetypal number relating to the lunar cycle, because the lunar cycles, there's actually 2 of them. The amount of time it takes for the moon to go around the Earth once is the sidereal cycle, 27.32 days. And then the synodic cycle, that's what we see with the lunar phase, that's 29, or just over 29.5 days. Now, I mention in my book how these 2 measures, 27.32 is rounded up to 27.333, so 27 1/3. And the 29.53 is rounded down to 29.5. And those 2 numbers both feature in the staircase that leads up to the chapter house at Wells Cathedral. Now, again, I won't go into more detail of that, but that's all in the book, in the chapter about the moon. Right, so let's look at these 2 measures, the 14 and the 28-fold division of the circle. Right, so I'm going to stop sharing my screen and I shall switch. Hello. Now, I'm in different surroundings today. I'm actually at a friend's house in Whitby, and so hence the different surroundings. Now, I've got as many lights as I could around it, so hopefully there should be enough light to see this, but I'll also be pressing heavy with my lines to make sure you can see it. Right, I shall get my drawing camera in place. So this is how you see my work. I've got one of these sorts of cameras that looks down onto the table. And I'll spotlight myself for everyone as well. Okay. Right, now the actual divisions that you use for 14 and 28 is by dividing the radius into 9. And then for 14, you basically use 4/9, and for 28, you use 2/9. Now, they're both really good approximations, and with the 28-fold division of the circle, we're actually going to sort of divide the circle into 4 and then do each quarter of the moon, you could say, each 7-day week. So what we need to do is to get these nines. What I'm going to have us do is have 4.5 inches as our radius. Now, 4.5 inches, obviously that can be divided up easily into 9.5 inches. So that's what we're going to do. Four and a half inches. Now, with this 14-fold division of the circle, when we draw our circles in, we will some of our circles will go slightly off the page, but that's not really an issue because we've got our we've got the divisions of the circle, which is really what we're needing. Right, I'm gonna do this first just to make sure it comes up as 4.5. Yeah, okay, so I'm gonna go with that. 4.5 inch radius. Whenever I travel, I was traveling for work. I was teaching in Manchester a couple of days ago, and so whenever I do something like that, I always get the chance to go somewhere to do some measuring. So I was measuring the beautiful geometric floor tilings in Byland Abbey on the North Yorkshire moors, and that's why I'm now up in Whitby. Now, the measures there, they were pretty much all English feet. It's really interesting stuff. I'm going to have to do a whole thing about Byland Abbey now as well. So that's yet more stuff to write about. Now, with this one, having taken that 4.5 inch measure, I'm now going to get 2 inches on the ruler. Now, as ever, to guard against sort of a gradual accumulated error, I'm going to go halfway around the circle and go back to the top and go the other half around the circle. So having taken that 2-inch measure, now this first circle is going to go off the page, but don't worry about that because it's the division of the circle, obviously, that we need. But I haven't gone down this far. I haven't gone sort of to the bottom of the circle. I'm now going to go back up to here to carry on from here. And like I say, this helps a little bit with stopping the build-up of accumulated error. Because obviously, if we keep on going round the same way, and it is going very, very slightly out because it's just a rational approximation, then it'll keep going out more and more and more the more we go around. Whereas by going back up to the top, we've sort of gone back to our initial circle. Now, mine's definitely gone off a bit. You can see it hasn't quite met. So it's close, but a little bit off. But the one that I did before was bang on. So there's always that slight little build-up of inaccuracy that can happen, but doesn't always happen. Now, I'll leave you to use this as something that you can draw stars with. So obviously you can turn your paper over if you put pinprick holes in. And then you can go through that same process of missing a particular number of points and then drawing a line. And you can get lots and lots of stars with this division. So I'll leave that to you. If you want to know how to do that, this is the first one of these sessions you've been to. If you look on my YouTube channel, you'll find me sort of drawing polygon stars and describing how they're done in some of the earlier sessions, particularly the first one and the third one. Now, I'll leave you to do that yourself because I want to show you the 28-fold division. Now, one way of getting a 28-fold division would be to also take these vesica shapes here and put your ruler through the middle like that, and then you can just halve the division like that, and there you have the division. So you can obviously double what you have from 14 to 28. But we're now also going to actually look at the 28-fold division of the circle too. Now, before we leave this one, perhaps I'll write down exactly what it is we've got here. So 14-fold division of the circle, the actual proper measurement for it, if the radius is 1, then this is the actual edge length. And it goes on and on. So this is it to a few decimal places. And so what we've done is essentially taken 1 and divided it by 9, which gives us 0.11111, and then multiplied by 4, 0.44444. So that, as you can see, is very close to this. So that's why we can use it. Right, let's now do the 28-fold division of the circle without just doing that sort of doubling that I just described. I'll actually divide into 22, or 28 rather. We need to begin with the same size of circle, which is 4.5 inches. Now, all of these circles that we're going to draw will stay on the page because obviously the circles we're going to be drawing are going to be smaller because it's a larger division. Now, again, I'm going to check that it is 4.5 because sometimes even when you check on the ruler, yeah, okay. Right, now with this one, with a 28-fold division of the circle, if the radius is 1, then the edge length is this, 0.22392, and again, it goes on and on. So as you can see, what I'm going to do is just turn this into 0.2222, and so you get the repeating decimal. Now, bearing in mind that that is 2/9, what we need to do is we've got our 9 half inches, 1, 2, 3, 4, 5, 6, 7, 8, 9. And we're going to go down to 2/9, which means we just go down to 1 inch. And that gives us our 2 half inches. Now actually, I've just remembered, I'm going to get us to do something first before we use that measurement. I'm going to get us to actually divide this circle up into 4. So we're going to actually put the compasses onto another measurement. Now, first of all, if you've got your paper in landscape orientation, so we can fit the bisector crosses in here and here. That's why I'm drawing the first line through the center of the circle from top to bottom, like so. We're going to divide the circle into 4. I just forgot before I put the compasses to that 1-inch measurement. So to do that, we'll need to go back to our original radial measurement. So rather than getting that from your ruler, get it from the circle that you've got on your page. In fact, no, sorry, I've changed my mind. I'm actually going to open up the compasses to a slightly bigger measure like this. That depends on how big your compasses go. What I'm trying to do is to keep the bisector crosses sort of outside of the circle. Now, if your compasses aren't quite large enough, it doesn't matter if the 2 crosses you make are here, but try and keep them away from the circumference. So put the 2 crosses either here or beyond the circumference. It's quite a large measure, so you might need to, so, if you need to, you can do that. Put a mark inside. But as long as the measure that you use from either one of these points is the same from there to there and from there to there, then it doesn't really matter what measure you use, because you'll end up with your crosses along the axis that we want to mark. And once you've got those bisector crosses in, we want to put, and we only really need this line to go through the circle. Now, the reason for doing this is because it really helps to cut down on the accumulated error, accumulated inaccuracy. Because you can imagine, if you've got 28 circles, if you've got 28 slight inaccuracies, it really is going to start to go off. So what we're going to do is have each 7. So it's rather nice. It's like a lunar cycle, because you've got the 28 as the whole cycle, but you've got 7 in each one of these quarters. And so rather like the 7-day weeks that you get, the 4 weeks that you get in each month. Because of course, month comes from the word moon, if you haven't realized that already. Now, once you've got this line in, you don't actually need these crosses anymore. So I'm actually going to get rid of mine, because they're going to, they're not going to cause a big problem, to be honest, but it just will neaten it up, because our small circles are going to go into that area where the crosses are. So you just need those crosses temporarily, really, to give you the bisector. Right, now we can go to the ruler and take that 1-inch measurement, which is 2½ inches, so our 2/9 of the circle. Now this way, if we do begin to go slightly off, then by the time we've done 1/7, then we can sort of go back to being accurate again, because we can go back to one of our quarters. So it sort of cuts down on that accumulated error. Now, also, how nice that we're drawing 28 images of the moon. Like, these are the 28 moons which we're drawing in with these 28 circles. Now, there's 4 circles that I've drawn there. Now I've drawn 1, 2, 3, 4. I'm actually going to begin from here and move in that direction. So that helps even more with cutting down on accumulated error. Yeah, and this gives a really good, accurate division. So there is one week's worth. Now again, having got 1, 2, 3, 4, I'm going to come down to here. And this one's definitely gone up a bit on this particular quarter, so I'm going to compensate for that. Now, the whole of the cathedral at Wells, as far as I'm concerned, is marked out with rational measures. Units, feet and cubits. And in fact, as you can see in that particular part of my book, there's 3 different foot units, which will have musical relationships. And so this is really how you get the music, because as you may be aware, with the quadrivium, music is one of the 4 subjects, and to have musical ratios, you need rational numbers. And so that's how you get the music coming into the design, by having these rational units, which, as I showed you in the slides, approximate irrationals, like that 153 over 200 for the octagon. And so you have your 28 moons. Now, of course, you can subdivide in a similar way to what I showed you with the previous one. So you can go from 28 up to 56. And circle of 56 is quite an important one. Again, you find that in Stonehenge and various other places. Right, I'm going to go back to my face camera. As ever, this session will end up on YouTube, so if you need to go through any of these processes again, you'll find them on there. Now, while I'm here, I might as well mention that I'm I'm finally getting myself organized to run a course about my book. It'll be a Cosmos in Stone course, and it'll be in the city of Wales, of course, because that's what the book is mainly about, the cathedral in Wales. It's going to run, actually, I think over the 8 days of Easter. It's going to run from Palm Sunday to Easter Sunday, and as well as lots of study, there'll also be walks. There'll be a full moon walk for the Paschal full moon. There'll be an Easter morning walk, obviously weather permitting. We are in the UK. But it'll be a mixture of study, eating together, walking together, from Palm Sunday to Easter Sunday, which is from the 24th of March to the 31st of March. And then the clocks change for that. So we'll get this more light immediately after the course finishes, which is quite nice. The Annunciation is actually on the full moon, on the Monday in Holy Week. So I'll put some information out about that very soon. And you're welcome to come to Wales and join in with that. Right, now I'm going to just finally share my screen to give you an image of the next session that we're going to be doing. And there it is. So we'll meet on the new moon. Now this one's going to be 11 o'clock in the evening. I am going to stick to these times of the new moon and the full moon. There is actually going to be one about sort of 3 in the morning in May next year, so that should be fun. I might not be at my best then, but for people in other countries that might actually work quite well. So the next one, 11 o'clock in the evening on Tuesday in just over 2 weeks' time. So hopefully you can come to that. As I say, all these sessions are going on to my YouTube channel, so you can look them up there to go through them again. Okay, thanks for coming, and I hope you have a good day wherever you're spending it.